Hello?
Test, hello?
Good. You know?
Great.
I'm going to...
Turn the lights off, I guess.
Yeah, we can turn them off.
Excellent.
The windows open.
Perfect.
Won't be too bad.
Great. Did you want this quickly to do an intro?
I'll do an intro.
Okay.
I'm just going to speak loudly, but
Sure.
I guess so that everybody can hear.
Yeah.
Well, thank you all for coming. Welcome to Daniel Violette's thesis talk, to be followed by his thesis defense, which will take place when we're done with the talk and questions. So let me introduce Dan. Dan has been a remarkably effective experimentalist. And those of us, John is one of my fellow kin in the experimental world, we want more students like this guy and like John's students. So it's a pleasure to introduce Dan, and he's going to tell you what he's done. I'm not going to steal his thunder, but he's done some remarkable things, working with our lab, which has been developing imaging wide-field X-ray telescopes for many years. We've flown them on balloons. We've proved a lot of technology that hadn't been tested. And Dan will tell you about this, so I'm not going to say any more, but his timing is perfect for what he has done for his thesis, because we are planning a proposal, a significant proposal, which, if we get it, would be wonderful for the CFA, for a small Explorer mission. That's a NASA mission. That's the Explorer program, which is the original program for space science at NASA. And so I won't tell you more about what that will look like and what it will be, but Dan's timing couldn't have been better to get us to the point we're at. So Dan came to us from the University of Connecticut, where he did his degree in engineering physics. So he's a very capable engineer, and he knows his physics. So it worked. He's got mostly an engineering-related talk, so bear with that if you are, not so excited about that. But I think you'll get excited when you see some of the things that can be done. But he's going to conclude his talk, and then I'll stop saying what he's going to do, because he will do it, with some interesting discoveries of a new type of variability in black hole X-ray binaries. It's been suspected before, but Dan, I think, has made it convincing, and there will be a paper or papers to follow to let the whole world know about this. So I'm not going to take any more of your time, and Dan, take it away.
Thank you. So just quickly making sure that this is working. Well, hello, everyone. I'm glad to be able to explain my thesis work to everyone and to present my thesis work. So while here at Harvard, I was working on optimizing our cadmium zinc telluride detectors for our soon-to-be proposed wide-field X-ray telescopes to discover more high-energy transient phenomena. My advisor, Jonathan or Josh Grindley. Josh, you have helped me so much over the years, and I have a little fun story that I don't know if you remember. When I was originally accepted into Harvard, but before I had come for my visit, I one day get a random call out of the blue from a number I don't recognize. And on the phone was Josh Grindley telling me how excited he was that I had been accepted and how much he would love to meet me and to talk about what he was doing in his lab. And I will always remember that conversation, and I'm really glad that we've had a chance to work, and I've had a chance to learn from you over all these years. So thank you very much. As I continue on, I must say thank you to all my family and friends who've really supported me over the years and have just helped out immeasurably to keep me sane and to just keep loving me and to keep supporting me and to just being there for me, and it made life worth living. So thank you very much to everyone. I also need to thank the Harvard community, both the faculty and the graduate students. I need to thank the admins who helped me out so much, Peg, Stephanie, Rob, who's now retired, who all just have helped me with so many things, from taxes to reimbursement to scheduling this. So thank you very much. I need to definitely say an extra thanks to the folks I met in AY2, or the Celestial Navigation class, which I taught here for several years. Max Mulhern and Phil Sadler, who are both wonderful people to work with and really helped me develop my love of teaching, especially, and really get involved with the undergraduates, which I had not done before at Harvard, which was amazing. Beyond that, I need to thank Chris Moore, who was an awesome mentor. Thank you so much, Chris. You really looked out for me. You did a really good job of making sure that I wasn't just thinking about the details of the research, but thinking about the larger picture of where I wanted to go with my career. And for that, I will always be thankful. So thank you very much. And lastly, I have to thank the research group I worked with. So Josh, Brandon, Jason, you guys were all amazing. I saw, there, where did he go? I saw Brandon earlier. Anyway, oh, there you are. I have to say thank you so much. I've learned so much from all of you, and it's been a wonderful experience just developing this instrumentation with you and having our lab meetings and really just working on things together. So I'm very thankful for all of you. And finally, I have to thank my committee, especially Doug and Fiona, who are not present, but hopefully watching live from very different parts of the world, who are here observing and watching on times that aren't typical. So thank you very much for both of them. I have to thank John for being my committee chair, and Ramesh, thank you as well for sitting on my committee. And once again, Josh for sitting on my committee, and for being my advisor. So to start broadly, our universe is in a constant state of change. And as we observe these changes, we learn a lot more about how our universe works. And when you think about universal change and the scale of how the universe progresses, you might think in terms of billions of years, or millions of years, or hundreds of thousands of years. But there are quite a few processes that occur at extremely fast periods of time with a lot of violent and high energy and force. The field of time domain astronomy seeks to discover, characterize, and explore these transient phenomena. These processes can occur anywhere in the sky at any time, so you need to be ready to spot them, otherwise they'll be gone before you know it. So these processes occur from minutes down to seconds or even sub-seconds, so extremely quickly. Examples of some of these processes include X-ray binaries that produce these brilliant flares and outbursts as they accrete matter from a stellar companion, long gamma ray bursts, which are formed during the collapse of massive stars, short gamma ray bursts, which we now know that can be produced from the collision and the collision and merger of neutron stars and black holes, as well as lots of different kinds of phenomena that can occur, around the center of galaxies around supermassive black holes. Now, many of these phenomena, in fact, all the phenomena I listed, are visible in the X-ray and gamma ray energy band for electromagnetic radiation, which makes it ideal candidate to focus on with developing astronomy instrumentation to discover these events. Here's an example of a really cool X-ray telescope. So this is the Nuclear Spectroscopic Telescope Array, or NuSTAR. This is especially special because Fiona, who's on my committee, is actually the PI of this mission, so it's extra cool. It uses grazing incidence mirrors to focus light onto 4 detectors that are separated from the mirrors by pretty long distance because of the low focal length. So you can see how long this telescope is. And this telescope achieves incredible sensitivity and spatial resolution, but has a very narrow field of view. So you can kind of equate this to looking through a pair of binoculars or something, where you see something very well when you look through a pair of binoculars, but the surrounding space, you don't see, everything else is obscured. And if you're looking for these events, these transient events that could occur anywhere, you really need a wide field instrument. On the bottom right here, I just want to introduce one of the 2 telescopes flown on NuSTAR. They're each 4 detectors, which are cadmium zinc telluride, similar to what we're working with, and are flown with application-specific integrated circuits. These are the readouts of the detectors, and you can think of them as little pieces of silicon where we squeeze all the circuitry and the capacitors and the other bits and pieces that we need to do the readout into a single chip. And that sits right below these detectors. And this is all pixelated. So I'd like to introduce the High-Resolution Energetic X-Ray Imager Smallsat Extremes Explorer, which is a mouthful, but it's HSEE. And this will allow us to detect and study transient phenomena, and this is what we hope to propose at NASA. On the right here is a model of the telescope I've developed, so you can see it kind of in its full glory. Now this is a coated aperture telescope, which provides a very large field of view using this tungsten mask with a bunch of holes in it that I'll explain on the next slide. And this is over a steradian field of view, so this is like a tenth or a little bit less than a tenth of the field of view of the sky. and has pretty good source localization. So you can kind of find these sources with this telescope and have other larger telescopes follow up if you need to. And then below here, what you see is this array of cadmium zinc telluride detectors, which are basically identical to the ones flown on NuSTAR. They're 2 by 2 centimeters each, and they provide this very large imaging array for this telescope. Now, the reason we use so many detectors compared to NuSTAR is because we do not have focusing optics to focus light onto our detector. You can think of this as a house with gutters that's all emptying its rain into a rain bucket. You have a large surface area that's emptying all this water into this one bucket. But in our case, we don't have that roof, so we just need a larger bucket. So we design a larger detector plane. This is coupled with the fact that since we are seeing larger parts of the sky, we have larger backgrounds that are coming from something called the cosmic X-ray background, which introduces other photons we don't care much about. So we need to make sure we have larger area to be more sensitive. So now I'm going to explain how a coated aperture telescope works. In its simplest form, you can think of a single hole in an otherwise opaque mask and how light can pass through that hole to project an image on a plane. Now, while this could work in practice, a single small aperture hole in an otherwise opaque mask would basically cut off 99.9% of your light. So how do we fix this? We just drill more holes. So ultimately, what we're looking for is approximately a 50% open, 50% closed mask with a bunch of holes in it. And depending on where the location of the star is or the source is, as it shines onto the detector plane, it'll produce a different shadow pattern of the detectors that are visible. And when you stack up these different patterns, you get a detector image. And by correlating this shadow pattern or this detector image back with the mask pattern that we have good knowledge of, we can reproduce the sky image and determine where the sources are. Now I'm going to talk a little bit about the detector itself of the HSEE telescope. So like I said before, this is a cadmium zinc telluride CdZnTe detector. It's a pixelated detector with over 1,000 pixels. So each of these are like 0.6 millimeter pitch pixels, and there is a 32 by 32 grid, so over 1,000 pixels. So lots of different photon channels that can be interacted with. And this is a high Z material, so it has really good stopping power for the energy range we care about, which is 3 to around 2 to 300 keV. And these are all read out by a pixelated NuSTAR ASIC, which once again does all the readout and amplification of the signal from these photons. And you can see below here, we have decided to do basically a 2 by 2 building block for our detector. It's a modular array. We call these 2 by 2 building blocks the detector crystal arrays. And the idea is that we can put these together in such a way that we can build up a full detector plane or multiple full detector planes if we want to fly multiple telescopes. So here's a bit of a zoom out shot of the full detector that we are proposing for HSEE, where you can see kind of a part lifted off to show the aluminum bench that all the detectors sit on, and then the readout front end, the system that sits behind it. And it's important to note that there are quite a few detectors here. NuSTAR flew a total of 8 detectors, and we plan to fly 256. So it's extremely important that the process of integrating these and testing them and putting them into a full system is as efficient as possible. So to that end, I've developed equipment here while at Harvard to improve the testing and characterization of these detectors. I've also explored the effects of adjustments to the NuSIC internal parameters to determine basically a set of parameters that will best work for our system and hopefully streamline the whole testing and calibration process that we need to go through. So here are the two main components of my development work in terms of these systems here at Harvard. On the left, we have the ASIC testing stand, which is a system used to test bare new ASICs prior to bonding them to any detector medium. And we do this in order to screen out bad integrated circuits before bonding. So this is important because we don't want to ever bond a bad circuit to a good detector because it's a waste of material, and we only have a limited supply. We're making a lot of these. On the right here is a thermal vacuum system, which is very important for confirming that our devices and our detectors are going to work in space-like conditions. These will hopefully eventually fly in space, and you really do want to make sure you're testing them beforehand to confirm that they work. So a couple more details about the ASIC test stand. Originally, the new ASIC has only circuitry on the top surface. So you can imagine that there's over 1,000 pixels spread out on the top surface of the ASIC, And then there's a separate 87 readout, commanding, and power lines that must be connected to read out and operate the detector. Traditionally, and on Neustar, this was done with wire bonds, very thin gold bonds that were connected to the new ASIC and then a front-end readout board below. These bonds are very delicate, tightly packed. It's like 225 pitch bonds, and ultimately are very sensitive. So assembling a couple of these at once is not a big deal. But now we're talking about over 200 of these that are very closely packed. You need to be very, very careful of messing up those wire bonds by accident. We've proposed using through-silicon vias, which instead of wire bonds, uses direct copper channels right through the new ASIC, the silicon of the new ASIC, to reach the backside of the device. And by basically doing a flip chip bonding where you take your device, your new ASIC device, and just solder it directly to a readout board below, you can eliminate the need for all these delicate wire bonds. The introduction of this solder processing introduces these solder balls, which are in red, and the introduction of these makes it difficult to test these ASIC devices with the traditional wafer-level probe card testing. So rather than using these probes in a probe card, we had to come up with another way of doing this testing on the diced ASICs. This leads into the ATS. Here is an example of the ATS where it's making contact with a bunch of these spring-loaded microprogo probes that we use on top of a surface of an ASIC. So here's the bottom surface of the ASIC with solder balls. I'm going to actually use this for the people online. So here's an ASIC surface, and on top of that ASIC surface, we have a row of two rows of staggered solder balls from all 87 of these readout pads. And we're making very good contact here, as you can see, with these crowned readout pads. And on the left, there's just a bit of an image. So here's an overview of this device. We have both a planar translation stage as well as a rotational alignment stage that basically helps us match the 87 rows with the probes exactly, since these are very, very small, and that we expect some die-to-die variance between the integrated circuits, so we must have this alignment. And then we also have the vertical translation stage, which allows us to lower and raise the probes in a controlled manner. The ASIC itself sits on this platform in the middle of the image, which is this yellow electrostatic dissipation plate, which basically prevents us from accidentally shocking the device and ruining the integrated circuit during test. This all sits on top of a vacuum chuck, which we haven't had to use, but allows us to really have a good secure hold on the ASIC. And this is all read out through this field programmable gate array board readout system, which is just a fancy word for a programmable piece of technology that lets us program and do all the data analysis and handling for the device. Next, I'll just briefly describe the thermal vacuum system. So here's our thermal vacuum chamber that I've worked really hard to build. You have most of as I mentioned earlier, this is important for testing detectors under space-like conditions. So this is testing now, rather than just the new ASICs by themselves, fully integrated detector and new ASICs, the full detector system, so the full detector system. And the space-like environment is one of extremes, both extremes hot when you're in the sun and extreme cold when you're in the shadow of the Earth, and therefore you need to really be able to walk your detector through a range of different temperatures and conditions to prove that it'll work. So all the power, data, and thermal and vacuum monitors exist in the bottom plate of this chamber below. And we're doing the cooling with this water ethylene glycol mixture, which is basically antifreeze, which lets us get to testing around 0 degrees or a little bit cooler, like -5 degrees Celsius. And then at the top, we place our X-ray transmission window and our X-ray calibration source, which lets us calibrate and characterize our detectors. The system inside looks like this. So this is the current system that I've developed and put together. Below, you have a cooling plate that is with the antifreeze running through these coolant pipes. And on top of this sits in the center a detector crystal unit board, which runs a single CdZnTe plus new ASIC detector. On the bottom side of the image, you have a high voltage board that provides a bias for our detector. And on the top side, you once again have that field programmable gate array board that does all the readout and everything that sits behind a power isolation board to make the noise of the system more manageable. Great. So those are the two large equipment developments I did while I was here at Harvard. And now I want to talk about my work optimizing the actual detector performance with the new ASIC in a mode called charge pump mode. So understanding how the detector works kind of follows as this. So photons will be passing through our coated mask and interacting with our semiconductor material. Electrons are excited through the band gap in the semiconductor into a conduction band, as it's called, making this kind of electron plasma that lives in the lattice. And when you apply a bias to this plasma, both the electrons themselves as well as the vacancies formed by the lack of these now excited electrons, called holes, drift to the cathode and the anode respectively. And as these reach the cathode and the anode, this generates a current in the pixelated new ASIC channels below. So once you generate this current, this signal current, we can now talk about what is happening inside the new ASIC. So this is a bit of a complicated figure, but I just want to quickly point out that the important thing to take away from this is what is being changed to optimize this device. And those are the parameters within these two boxes. You have the VNL1, VNL2, and 4V cell, and the VPL2 and the VPL3. And these are settings that I'll be explaining in more detail, but that's the important takeaway. So as the signal current is passed into the system, it runs through a preamplifier, which amplifies the signal and lets us basically measure it more effectively. This preamplifier has two outputs, a voltage output and a current output. The voltage output is passed to a shaping amplifier, which it does as it says. It shapes the pulse into a way that can be read by a voltage discriminator, which then decides if the pulse height is high enough to indicate that this is a real event to trigger on, or a real photon. Once it realizes it's a real photon, it starts a trigger out process, which then begins the readout of the new ASIC device. In the meantime, on the current output side of things, this current output is passed back to the preamplifier input to set the signal gain, and is also provided. A copy of this is provided to a readout circuit, which is basically a bank of capacitors that sequentially measure that current and set their charge based on that current, which then can be read out once the trigger is set. So over my thesis work, I've focused on modifying and adjusting these 5 parameters. So the parameters, the VNL1 and VNL2, modify the preamplifier feedback, which primarily adjusts the bias, the standing current in the preamplifier output. And this can impact the energy of the detector, because as you increase the standing current, you basically are introducing more shot noise into your system, which is increasing your readout noise and degrading your energy resolution. The shaping amplifier output is controlled by the VPL2 and VPL3 bias voltages. And this will probably modify the energy detection threshold of our detector. So as I was saying, the shaping amplifier really controls whether you're triggering or not on the photon, and by changing these settings, you can kind of modify that trigger capability. The new ASIC has a secondary operating mode called charge pump mode that will modify this feedback network by basically modifying how the preamplifier feedback works to return about a 20th of the total current back to the preamplifier input. And by returning a lot less current, you're also affecting the amount of standing current, and you're really reducing your readout noise. This is done by using this capacitor, which acts as a feedback capacitor that must be periodically reset to recharge the capacitor, as it's basically trickle charging the preamplifier input. This is recharged on approximately a 1 millisecond cadence with a 4-volt voltage reference. And adjusting this exact value of the 4-volt voltage reference is performed with the 4V cell new ASIC internal parameter. So this is the 5th parameter. And this parameter can be used to adjust something that is called voltage ramping in the preamplifier output. So this is the description of the new ASIC operation. And now I'm going to quickly talk about what an analog output from the system will look like. So both of these images are an analog output, basically a debug line that's taken from the preamplifier output of a new ASIC with a induced trigger event. So this is driven by an internal test pulsar. On the left, we have 2 lines, one in black, which is the normal mode operation, and then one in red, which is this new charge pump mode operation with a different kind of feedback network. The baseline, or basically just the value of this, the voltage value of this flat surface, can either increase or decrease as you modify the VNL2 and the VNL1 settings. Likewise, in charge pump mode, you also need to consider this slope. So as you see, this is no longer flat in charge mode, but ramps up over time before the voltage reset, the 4V cell CPM reset readjusts it. And really, you do not want this voltage ramping. If you don't do resets often enough, this can really climb very high and drive your system to a nonlinear state. So ideally, you modify the 4V cell to minimize the slope or to get the slope to 0. Zooming in a little, the gray section at the center of this image is an example of what an event readout might look like in the analog line. So in blue, on the right-hand image, you have the remaining part of the baseline, and then you have a rise, which is where your trigger occurs, and you have your event readout, which basically stores a bunch of your measurements of the signal on a capacitor bank. And then after that, you have some post-event processing, but really the important parts of the baseline and then the event sampling. And we can look at this in a digital from the digital output as a series of S-curves. Now, the reason we use digital over analog is because digital really lets us record the data better, it lets us stack the data, and ultimately do the science we care about. Analog is simply a tool to figure out what's going on within the device. So the digital is the most important part. Here you see, once again, you have the baseline values that are being read out in the capacitor bank. You have your signal plus baseline values that are being read out after the trigger. And then the delta here, or the difference between the baseline and that signal plus baseline, is the strength of your signal, or your energy. So what this is doing is letting us simulate photon events in our system and read their energy. And what we're trying to do is improve this energy resolution as much as we possibly can. So on the left here, so both on the left and the right, you have these pixel gain plots. Really, when I'm saying pixel gain here, you can just think of this as energy. So, or if you prefer to think about it in wavelength or frequency, you can think about it in that way as well. So really what we're trying to do is we're trying to get these as narrow as possible, which allows us to glean more information from our energy spectra. So from a bunch of neighboring lines and stuff, we can learn more. So they're not overlapping and hiding each other. So in normal mode testing, I could show that by modifying these two register values, you can change the resolution of the energy resolution of the new ASIC pixels pretty dramatically. So it ranges from 0.8% of the full width half max down to 0.53% full width half max. And this is pretty significant, but it's important to note that on the right here, you can actually see what is happening when you turn on charge mode. Charge mode actually has much better energy resolution by a factor of 3 approximately. And also is relatively agnostic to choice in the VNL1 and the VNL2 settings, which is quite interesting. It's not something we knew before we started doing this testing, which is pretty cool. And it's something that will be fun to explore more. The mapping of the slide colors basically correspond to the V. So V is the VNL1, and VNL2 is O in this case, just because the actual parameter names are a bit different. So in this case, we had best results at approximately V3, so VNL1, 3, and then VNL2, 1, which are just register settings for these values. Great, so we've shown that we've achieved pretty good energy resolution in charge mode. Now we need to address this voltage ramping on the baseline. So minimizing this baseline voltage ramping, like I said, will keep us in a safe operating regime as we're running our device. And it's important to note that this optimal 4V cell value is going to be different for each pixel of the 1024 pixels on the new ASIC device. And so therefore, picking the best global 4V cell setting, because there is only one setting, you must pick it globally for the entire device, isn't extremely simple. You must either, you need to decide on a strategy. So using the analog readout, you can either optimize some pixels near the center of the device, and hope that kind of explains the ensemble of the pixels, or you can pick random scattering, or you can go from corner to corner. So there's a bunch of different ways you might be able to do this. Ultimately, this is still just very inefficient considering how many detectors we want to fly, so over 200 detectors. So by incorporating the CPM reset phase information alongside other timing information in our digital readout, I've been able to take this data, this phase data from the charge mode reset, and and provide a tool for us to do this with the digital data. So on the left here, we have, again, an example of the analog trace with a pretty significant voltage ramping over time. And on the bottom, is the plot is labeled by the CPM reset. So every time the charge per mode is reset, it goes back to 0. So it's a 1 millisecond cycle. And on the right, by mapping the baseline value of the digital readout to the phase information, we're able to reproduce the slope data in the digital readout. Now, this is really, really important because it means that we can now look at all pixels in the entire device together. So we're no longer, required to use an analog debug line to look at pixel by pixel to do this optimization. We can now do this optimization over the entire device, or an entire DCA, which is a 2x2 crystal, or an entire detector plane at once. So this is a phenomenal improvement, which will certainly help us pick these values effectively for our detector. So example of how you might do this on the right here is you have a pixel that has been run through a bunch of different 4V cell register settings, and then data's been collected digitally, and then once you collect that data digitally, you fit the slopes, like for example on the left, and you can plot those slopes along the register setting value, and you just do a linear regression, and you figure out where that intersects 0, where its slope is 0, and that's how you pick your optimal value per pixel. And by just summing these slope values across all 1024 pixels, you can really figure out where the slope of the entire device is minimized. And on the left here is just, again, another example of this, of like a well-chosen 4V cell value that's now being observed with the digital data showing how flat it is. So we've taken all these optimizations, and we can now go and characterize our detectors under thermal vacuum. So here we have data from CdZnTe plus NuStar detectors in our TVAC system, which operates at approximately 0 degrees C with 10 to the minus 6 torr, both in normal mode and in charge pumping mode. So normal mode is in red, charge pumping mode is in blue. And we see a pretty significant improvement in energy resolution for both two different X-ray sources we use, which was americium, which has an energy line at 59.5 keV, and then iron, which has a energy line at 5.9 keV. And we actually see even a more significant improvement at lower energies, which is really, really great, because that's something we're trying to push. We're trying to push our energy threshold to continuously lower energies to basically broaden the number of astrophysical transients we'll detect, especially some examples of this, high redshift long gamma ray bursts, which will have their energy peak shifted to lower energies, or off-axis, short duration gamma ray bursts from the merger of neutron stars, because when they're off-axis beamed, then you have some softening of the spectra as well. So this is very important. It shows that if we are able to successfully trigger at lower energies for these photons, we should be able to do a lot of really good work with these detectors. So the final two parameters I'm talking about here are the VPL2 and the VPL3 parameters, which, as I mentioned earlier, modify the shape of this shaping amplifier output that is then fed into a voltage discriminator. You can think of the voltage discriminator as a simple level that basically decides that if you're above this set level, this is an event that we should trigger on, and basically, and then begins the photon readout. And this trigger level is modifiable. So to push to lower detectable energies, the idea is that you want to lower the trigger level so you're more sensitive to weaker, lower photon energies, which will result in these lower peaks. So if you imagine this is kind of the peak you want to trigger on, I'll use my mouse here for people online. In the red, then for very low photon energies, you want to basically figure out the best setting you can do in order to basically discern this peak from the surrounding, the preamplifier baseline noise before the trigger. And the incident at the top right is actually a distribution of the noise in the shaping amplifier baseline. And as of now, we're not really seeing much of an improvement in this noise distribution for charge mode over normal mode. So this was some initial results from a bare new ASIC. So we're currently developing a system to do this more deliberately and more thoroughly by improving our hardware and introducing a analog to digital readout on this line to basically take a bunch of data and figure out really the optimal settings for this and figure out how it affects the threshold. Yeah, and just on the left is an example of all the different settings that can potentially be used. And not all the settings, but a small range of settings that basically demonstrate how minor changes can really impact the structure of the shaping amplifier pulse. And at more extreme values can really change the pulse itself. So it'll shrink in value, or it'll get narrower, or it'll get wider. So those are all things that these values change. Okay, so now I'm going to change focus a little bit. Previously, I was talking about my hardware development and the optimization I was doing with the detectors here at Harvard. Now I'll be talking about some work I've been performing with searching of the Burst Alert Telescope Transient Monitor database, light curves, for flaring black hole LMXBs and quiescents. While black hole LMXBs typically exist in quiescence, they occasionally go into these high luminosity outburst states, which is when we discover them, because otherwise they're very, very hard to see, which are driven by these accretion disk instabilities. And this accretion disk instability model really doesn't explain very short duration flaring activity very well that might exist in these objects while they exist in quiescence. And identifying black hole LMXB flaring in quiescence could be very fascinating because it provides us with another method of detecting these sources that doesn't rely on these very rare or long reoccurrence times, decades to like I think up to 60, 100 years recurrence times of these outbursts. So to that end, I have searched archival data from the Burst Alert Telescope Transient Monitor database, which is a database that tracks survey data from the Burst Alert Telescope on onboard Swift here, pictured in the bottom right, and provides light curves for a lot of these transient sources. So there are some types of noises and some hiccups that occur when searching for these light curves. Here's an example on the right of a light curve from the BAT Transient Monitor for a black hole LMXB source called AO620-0. And what you see here in the center may look like an interesting event. So on the bottom you have a date, on the left you have the rate or the flux of the event, and you are curious about looking for basically rises in these short duration rises in this rate or this flux. And so what you see here in the center of the image might look like an interesting short duration event, but the data points are all in red. What does that mean? What this means in this case is that this data has not been has larger systematic error than you would like because the spacecraft has not been dithered. Let me explain what that is. So bright sources in the field of view of a large imager like a coded aperture field imager introduce a lot of spatially correlated noise or errors in your accumulated image. And these create a bunch of basically bright spots in your sky image that can be misconstrued as transient sources. And by dithering, which usually means either pointing the telescope in different ways or rolling the telescope to rotate the field of view, you basically smear out these accumulated positive increases. And while this is typically done for the BAT Transient Monitor, for the BAT instrument and for Swift on BAT, or BAT on Swift, it's not always done. And therefore, when you're looking for short duration events, you might be tricked by these periods of non-dithered data that basically lead to a bunch of systematic error building up in the sky pixels you care about. So using data from, and then a final thing I'd like to say is that while this flagging for non-dithered data is done by the BAT Transient Monitor, it is unreliable for data past 2013. So there's actually it looks like a break in the script following 2013, and you can no longer rely on that flag to tell you whether or not your data has been successfully dithered by the spacecraft. So using spacecraft pointing data from the BAT Transient Monitor, I have recreated this dithered flag for both dithered and non-dithered observations. So now I have a good sense of whether these observations have been dithered. And I've also updated the BAT Transient Monitor's procedure for applying a systematic error correction to the light curve data. So the BAT Transient Monitor applies two separate light curve corrections in their two separate data products. They have an orbital data product, which means that every orbit the spacecraft takes around the Earth, it produces a single point in the light curve for a given field of view. The daily product basically is combining all the orbital products for a given day. And basically what they found is that by looking at blank sky fields, they notice that places that should have a pretty normal distribution of around 0 is too broad. So they apply an error correction factor to basically account for this. So they apply one for the orbital correction, they notice that there's an increase, and they apply a larger one for the daily correction. What I've done is I've separated the data into a non-dither component and a dither component, and rather than treat the data products as an orbital component, an orbital data set, and a daily data set, I basically bin these observations by observation time, or total observation time. And for dither data, the bat transient monitor does a really good job of applying these corrections, because as you can see, from 0 seconds, kiloseconds, to a very large amount of kiloseconds, 10, 20, 15, 20 kiloseconds, the correction needed goes from the orbital correction value up to the daily correction value. However, for non-dither data, we need a much larger correction value in order to replicate this systematic error correction. And so really what this means is that up until now, the non-dither data has had a very underestimated error, which is one of the reasons that when I search for this data for potential flares, a lot of them crop up as false positives in my data set. So now that we've kind of accounted for these periods of no spacecraft dithering, I can then go ahead and reapply my transient search algorithm method. So I'm using the Bayesian blocks search method algorithm, which is a time series analysis method that is basically generating a number, is scanning the light curve and generating a number of change points or bins based off of the changes in significant changes in the underlying data. So whenever the data basically becomes significant, it will generate a new bin and bin the data, and from there we can assign a significance to that data point. This is a great method because it's relatively non-parametric. Unlike bat transient monitor, which has a orbital product and a daily product, I don't need to assume any fixed bin length or bin boundaries, which is nice. And also, I don't need to make underlying assumptions about what a model of a flare might be. So I don't need to model it with the fast rise or exponential decay or anything like that. So what I've done is I've searched a total of 30 black hole OMXB sources, 14 which are dynamically confirmed or known black hole OMXBs, and 16 candidates which we think might be black hole OMXBs, with this Bayesian blocks time series analysis method. And after performing this dither data correction, and then I find of those ones that I find of the discoveries I find that are significant, I generate stacked sky images, which for these very short periods of time. Now, this is not something that's been done before. This is something the mosaic, the tool to stack bat images, is generally used for the full survey pipeline. So there, up to this date, there's been no tool to really look at only a small window of stacked images to generate a sky field. However, I was working with folks at Goddard Space Flight Center and the BAT Transient Monitor team to basically repurpose some of that code to produce these short duration sky images. So here are some examples of this working really well. So here are previously reported flares from a black hole LMXB source called V44 SIG. These were previously detected and reported flares with astronomer telegram numbers listed here on the slide. And these are very short, so a fraction of a day, both are fractions of days. One's a tenth of a day, one's like a hundredth of a day in terms of the binning. And they occur approximately half a year after a massive outburst in 2015. And shortly after this, there's actually another larger flare that's very, very short. That's a several day flare a couple days later. And in the figures, what we see here is the data products from the BAT Transient Monitor. So we see the orbital data, which is in blue, which is kind of faint. And then we see in black, much closer to this baseline value here. In black is the daily bin data. And this is the case for both of these observations. And on the right here is one of these stacked images I've generated of V404 SIG with a couple other sources in the field. Here's a very interesting case. This is 4U1630 minus 472. This is a candidate black hole MXB, but it has frequent outbursts. Some of these outbursts tend to be very soft, meaning that the energies of these outbursts are below that of which can be imaged by a bat. So a bat is a 15 to 50 keV instrument. These outbursts are softer, and therefore sometimes are not always they're not always seen. However, what I detected was this increase in the bat transient monitor that was around 11 days. That started on April 3rd, 2008, which coincides right with the end of one of these soft outbursts that began in January 2008, and basically had a reduction in variance start like April 2nd. So basically, right as the outburst is ending and winding down, all of a sudden we see this hard X-ray increase, which is interesting. So what's happening here is that the source is entering back into a hard X-ray state. So less soft thermal emission, more hard non-thermal emission. And on the right here, you can see kind of the white label points to the very faint 4U 1630 minus 472 in this image with the surrounding sources. Here's one final candidate. So here's another dynamically confirmed black hole MXB, which has experienced very brief outbursts before. This is a case of a just shy of 5 sigma Bayesian block detection with the bat transient monitor Bayesian block search on March 3rd, April 2009, which ultimately only yielded a approximately 3.9 to 4 sigma source detection after recreating the sky image and running the bat tools for detection. So that's located in the center of the image in the red circle. You can see that there's some extended features, so it might not be believable as a source, but it's still very fascinating, and you have a bunch of bright sources that are kind of in the field around it, although these are saturated in this image, which is why they appear so big. Great. So to back up and discuss everything I talked about, I've constructed and developed 2 really important test fixtures here at Harvard for the further development and testing of our cadmium zinc plus new ASIC detectors, which are the ATS and the TVAC system. I've explored the optimization of these detectors by adjusting the new ASIC internal parameters to improve the energy resolution of our detectors and to potentially lower the detection threshold, which is something we're continuing to work on. I have successfully demonstrated a method to parallelize this optimization procedure for new ASIC charge mode operation, which is going to be a massive time saver and definitely help us down the line as we develop and build our HSCE telescope. And finally, I have looked through the bat transient monitor black hole MXB light curves to try to discover these previously undetected flare activities, and while doing so, really develop some methods to help improve coded aperture systematics, which will benefit both for future HSEE observations as well as conceivably other coded aperture instrument science operations. So thank you very much for your time.
Thank you, Dan. Very clearly expressed. Questions, comments? There's a lot here. You can either ask about science or technical aspects of what Dan has built and tested. But yes.
I don't know very much about coded aperture topics, but so you've described this with 2 planes. Is there any advantage or disadvantage of thinking about turning the coded aperture into a sphere and actually then having your detectors sort of pixelating them on more of a not a full sphere?
Sure. So typically, what we do for this type of detector is that we take our detector plane images and we do a Fourier transform with a mask, or I guess an inverse Fourier transform with a mask. But and I think by doing like one curved detector and mask, that makes it a bit more complicated. The math a bit more complicated than that. But what has been done is some examples of things we just thought about is rather than a curved system, you can do several flat segments that are added together that basically approximate the same curve, right, which might simplify it. Is it possible to do the curve? Absolutely. I don't know if the gains would be enough to really offset the added complexity.
Daniel, there's an argument for not doing it that way. if you make your detector plane looking at a much larger field of view, which is of course what we want to have, your background.
Yeah,
goes
you
up
do increase your background
enormously.
as well. Yeah.
So the better way to achieve what you could do with a curved mask and curved detector plane is to build multiple detectors with relatively narrow fields of view. And that's what this HC concept is all about. It's a stepping stone to then a medium explorer mission, which we hope to propose in the late 2020s, to put up 10 more of these telescopes. Dan didn't mention that what we're going to
I didn't.
propose are 2 telescopes, not 1, 2, on opposite sides of the Earth. And with 10 more, we cover the entire celestial sphere, which has never been done at any wavelength that I know of. The military may be doing this all along, for all I know. But that's the way to go. So,
Definitely, no, but it's fine. That exacerbates the need to assemble these things efficiently. So, yeah.
yes.
Yeah.
I had a question about the slide with the shaping parameters. You
Yes.
were showing a curve, and then kind of afterwards you had this like giant pit where you didn't get as many counts immediately after the actual trigger region. What is that? Why do you have you have this shaping at baseline, and then you dip way below the baseline? and all
Sure,
these
sure.
spaces?
So this is in terms of what this is. So you can think of this as kind of a time series. So this is an analog output. So this is just basically voltage that's coming out of the shaping amplifier. The shape of the output is kind of a black box to us. This is something that Rick Cook developed at Caltech. But ultimately, everything downstream from the initial peak can more or less be safely ignored by the system, because once you've, as long as there's no secondary peak that's greater than the initial peak, once you've triggered your detector readout, there's basically a lockout that prevents you from really caring too much about anything downstream. The only thing you must care about is how long your readout takes and how long it takes the baseline to return back to a stable value. So in this case, this is on a scale of 60 microseconds. I believe our readout, I'm looking at you, Brandon, is 10 milliseconds total for a 1 pixel event or 3x3 readout.
I don't remember.
I'd say around 10 milliseconds or so.
That's for multiple pixels.
Yeah,
so
sure.
You're on the millisecond time.
Sure,
So you're much
millisecond
farther
time scale, yeah.
than what you're showing here.
Yeah, so this is really a relatively small fluctuation, and really the most important part of this is the initial peak.
Yes, John.
Okay, I'll ask a question that I've wondered about for a while.
Yes.
As you've been describing your work. I hope it's a simple one. I don't know much about the observing strategy for these kinds of missions.
Sure.
So you've been showing how the lack of dithering introduces additional systematic errors that
Yeah.
you need to account for in analyzing the data from
Yes.
that data set. And that has future implications for future missions about wanting observing strategies that have appropriate offsetting and dithering so you can control those kinds of systematics that you explore. So why doesn't it dither all the time?
Sure. So it's kind of a twofold thing. For one, it's kind of just a operations problem. It's something that you must always. So here's the thing. So the Swift Bat telescope in this case, right? It has a narrow field instrument, which must, there's an observation campaign, and it wants to point at specific sources on the sky at a given time. So that really constrains what you can do by moving the center of the field. So because really you're always pointing out what the Swift UVOT or an XRT want to look at. Therefore, you're kind of limited to rolling. Typically, for normal planned observations, the instrument will always roll between successive pointings. However, there are cases where if there are basically interruptions in the observation campaigns because of transient detections or other automatic targets, or if there's a calibration target, sometimes those dithering steps are not performed by the BAT transient, the Swift BAT telescope. And while I can't really dig too deep into the reason why they didn't ultimately go back and institute that for every single kind of procedure they do, it's something that isn't done for those types of measurements, for those types of observations. So in reality, the systematic error buildup is relatively small, and for the detection of most transients, as long as you're attempting to do your best, it's sufficient. And for the BAT survey, which is basically adding in all observation time that the telescope has had at the entire sky, it's also sufficient because they're always looking at different parts of the sky and building this huge mosaic image. So that's the real reason for this instrument, why it doesn't always dither. I think if planning on flying a purely coated aperture instrument, I think the decision might be a little different in how you do your mission operations, because you're relatively agnostic to how you're pointing or where you're pointing, as long as you're kind of scanning the sky or if there's a transient that's in the field of view. And therefore, the way you design your mission operations, you can always be trying to roll or to repoint your field. And in fact, through this study, we found that it turns out that really you do want to be repointing the center of your field, because simple roll dithering doesn't always dither the field at the same magnitude, and therefore you can still get some of these false flags if you're not careful. So false positives if you're not careful.
Another short answer to that question. With a wide field telescope, it's very easy to just shift small amounts, and that's all this takes.
Yeah.
So it should be done by every telescope. And the reason it wasn't done with Swift, well, mainly because of the narrow field instruments wanting to be on target, but they've got fields of view that would have allowed small dithering. But the real answer is this had never been really studied before. There are no papers that present the kind of curve that you just saw and showed of non-dither data, the systematic error rate of increase. So this is new stuff that's going to get out in the journals where people will know about it. But in practice, this is easy to do for the wide field instrument. Just do this, just slight
You
offsets
just
in X
need
and
to
Y,
move a couple pixels. So.
and all this goes away for the most part. Other questions? Yeah.
Congratulations, soon to be Dr. Dan.
Thanks, Chris.
Yeah.
I'm proud
Keep
of
my fingers
how far
crossed.
you've come. I'm proud of how far you've come.
Thank you.
It's great to see all the great work you're doing. Can you go to slide 30? I have 2 questions for you.
Shoot.
Looks
Questions?
like you went a little too far. Slide 13, please.
Oh, okay.
13 is this slide.
30.
30.
30, yes.
My bad. I'm sorry. Yes.
So my question is on the spectral shape, particularly for iron 55.
Yes.
The asymmetry. It looks like you have low energy tails. What does that do to?
That is a good question. I think ultimately, I don't think it's too surprising that for an iron source or for any real source, you'll see kind of a lower energy contribution from either any kind of reduction from photons, either through the photon energy, either by you're either absorbing in you're either like getting ballistic deficit when you're absorbing into the medium, or perhaps there's or perhaps like you're interacting at near the top of your CdZnTe or something, and not all the electrons are drifting down to the anode pad. Or I can imagine a number of different, or even more basically, especially at with a higher energy. I guess this is why you asked for the iron, not the higher energy. For higher energies, you could expect other additional interactions that occur with photons, either with the chamber itself or with other things. But I imagine those can contribute to this lower energy tail.
Okay, so is one phrase that you can use to describe all those phenomena called incomplete charge collection?
I'd say that's good. I don't know if that's the full picture, but I think that definitely will contribute.
That
Yeah.
is the short answer.
For this study, are you reading out the neighboring pixels?
Yes. So
Okay, so
yes.
you're adding up the charge from neighboring pixels.
Yes. So okay. So yeah. So you're talking about specifically a co-adding. So if you have a split charge event, is that what you're referring to?
Yeah, I'm sorry. I had the same question, but I wondered whether the low end tail was.
Sure. So that is a good point. You could also have charge splitting or charge sharing between neighboring pixels. We do. Typically, we do 3x3 pixel readouts. So you have a central pixel that's triggered, and then you read out the surrounding pixel. In this case, we do not add it back in those. We had not added back in those pixels. I had not added it back in those pixels for determining if these are really responsive from charge splitting.
Okay, so my second question
Yes.
What is the biggest challenge you overcame during the thesis?
Oh my God. It might be kind of a little unrelated to my thesis work that I presented. I spent an Easter weekend at the Argonne National Lab doing some testing with the X-ray source there, and we brought our whole detector box. We assembled it. We brought it, and nothing worked. And I definitely was not the only one who was up late at night trying to figure out what was going on and how we can get data for the brief 48 hours we were there and bring it back. That was very difficult. That's kind of the fun answer. The hard answer is probably, I think, the pandemic. It was really tough being out of the lab and being away from everyone for over a year, or almost a year, I should say, not quite a full year, but and that really made it difficult to continue to develop the equipment. And then the kind of fallout of that is, of course, supply lines dried up, funding dried up, just other things really kind of got in the way of not being able to get to the finish line as fast as I was hoping. Another point I should say is it was very disappointing when we proposed our initial design for this telescope that it was unfortunately not selected. But that was also it was a fun challenge, and it was disappointing that it wasn't selected. So
This is a well-deserved PhD.
thank you.
Let me make another quick comment here. Dan not only came to us with a strong background in things that some of us were looking for, but he also impressed NASA in their new fellowship program called FINEST, and I forgot what the acronym stands for.
Future investigators in space science and technologies.
Yeah. So they opened this new, fellowship program, which was very welcome, and Dan got one of the very first ones. And so he deserves credit for that, and they certainly made the right choice, and it helped his work.
Absolutely. Yeah.
So, and the other comment I wanted to make, just I should have said in my introduction to Dan, he had some very interesting work that he was doing at Goddard, working on what became the NICER telescope. Some of you will recognize.
I don't know how much
that name.
credit I can take for nicer, but
It's not just something very nice. It's a very nice X-ray, non-imaging. So it isn't what we're talking about here, but it's very effective. It's up on the space station, and it's been doing great work. And Dan was involved with getting that built. And he's now going to go back to NASA when he finishes. He's got a NASA postdoc, very competitive program, and you'll be at Goddard working on higher energy gamma ray detectors, which relate very much to what you see here, but still higher energy. So if there are no further questions, I see one more. Yes?
I couldn't help myself. This is a very naive question.
Yeah.
In your technology work, you've got a very large number of very small bonds that are very carefully put together. How fragile is that at launch, when the whole mission is shaken? Because you haven't done a shake test yet.
So we haven't, but it's in the works. So thankfully we do. There is some heritage for this system that exists on NuStar, right? So some of the wire bonding techniques and stuff that they use is similar. In terms of how the whole detector plane is going to act, it's something that we're definitely exploring. We're looking into vibrational studies, just that are through computer-aided design, and also we will be doing some shake tests. And it's definitely a concern. You've really just got to shake it really hard.
It's not just some shake tests, it's all flavors of shake tests.
Yeah.
We have, as you know, Charles, a very strong collaboration with Lincoln Labs. They've got all of the equipment to do this the right way. We had debated building a system in our lab, or central engineering here does have some capability, lots of capability, but they could have done some. But Lincoln Labs can do everything under that you can imagine. And so we're going to very carefully test these things. But there's very little mass in these things, and so as you're undergoing extreme vibration, they're actually pretty robust. But we'll find out. No further questions? Yes?
So I had a very naive question. Can you go back to the slide you were showing the random filter for letting light into your pixel, into your sensor? I was just wondering, what's the advantage of having that randomized tungsten mass emitting light onto the detector plane in that shape, or configuration versus just letting all the light come through. I'm sorry, I didn't get that.
Yeah, so the reason we put holes, the reason we don't just let all the light come through is that that would not allow you to basically preserve. So you can think of it as a single hole, right? If you have one tiny little hole, right, with one single source coming through, it'll illuminate a very small part of your entire detector plane. And you'll basically be able to just geometrically trace that back to where the light's coming from. Or at least say a range of places where that light could have come from. Versus having the whole thing open where you really cannot pinpoint from any given place in the sky where it could be coming from. Yeah, and then you just do that with a bunch of holes, and you trace them back through all the holes that they can kind of come through, and you can rebuild your sky image.
There are other kinds of masks that do have not random patterns.
Yeah.
And they're very interesting. I actually suggested those patterns way back when. They're uniformly redundant arrays, they call it. And they have an autocorrelation function, which is a delta function, which is beautiful. That means you eliminate noise. But they have a big problem. They produce multiple images over a wide field. And that is not helpful. So a random pattern is the best thing. It averages out all the systematic noise. Non-random patterns can do these neat sounding things, but you pay the price. So it's, Dan, you want to say a word or two about how the masks are made for anybody interested in? There's a lot of interesting technology here that hasn't been mentioned, but.
So I mean, I'll say it brief. So basically, we're using tungsten, so it's a very high Z material, so it has good stopping power, basically opaque to X-rays with enough thickness. And these are very thin sheets that we are basically etching very, very tiny holes into.
Not we.
Sorry. Well.
Nearby by.
Yeah, an industry partner.
What are they called, Brandon?
Tech Etch.
Company that does
Yeah, and then we stack these to basically build up the thickness of the mask to basically be opaque to X-rays above the energies we're interested in.
Okay, I think we are going to
Great.
call this to a close. Thank you all again, everybody, for coming, and let's give Dan another round.
Thank you. Thank you. Yeah,